Across the globe, billions of devices interact and cooperate, forming vast, invisible networks that power the modern world. Distributed systems lie at the heart of this digital fabric, enabling everything from online shopping to real-time navigation and social networks. Unlike traditional computing, where a single machine executes tasks in isolation, distributed systems coordinate multiple independent computers to achieve a common goal. This fundamental shift offers remarkable advantages: scalability, resilience, and resource sharing, but also introduces unique challenges. Synchronizing data, handling failures, and ensuring security become intricate puzzles when components are scattered across different locations and networks. As technology evolves, understanding distributed systems becomes essential for grasping how our most critical infrastructures operate. To navigate this landscape, one must first explore the foundational principles that define distributed systems, the characteristics that distinguish them, and the motivations that continue to drive their development in an ever more connected world. Imagine reaching into your pocket, opening your phone, and searching for a nearby restaurant. Within seconds, you receive an answer, complete with maps, reviews, and directions. Or, think about streaming your favorite show, making an online bank transfer, or checking the weather through an application. Each of these everyday actions feels simple and immediate, but behind the scenes, an astonishingly complex web of computers works together, almost invisibly, to make it all possible. This seamless experience is powered by distributed systems, one of the most essential yet often overlooked foundations of our modern digital world. At its core, a distributed system is a collection of independent computers that coordinate their actions and communicate with each other, typically over a network, to achieve a common goal. These computers might be just a room apart or scattered across continents. Despite their physical separation, they collaborate, often appearing to users as a single, cohesive system. The essence of distributed systems lies in their ability to break large, complex tasks into smaller, manageable subtasks, assigning these to different computers, or nodes, which then communicate through messaging to solve the problem together. The shift from single, centralized computers to distributed systems stems from the limitations of monolithic architectures. Early computing often relied on a single powerful machine to handle all tasks, which seemed adequate when computing needs were modest. As demands grew, more users, more data, more services, centralized systems revealed critical weaknesses. A single point of failure could bring down an entire service. Bottlenecks limited performance, and scaling up required investing in increasingly expensive, specialized hardware. Distributed systems emerged as a solution, offering greater scalability, reliability, and flexibility by spreading tasks across many, often commodity, machines. One of the defining features of distributed systems is their scalability. Unlike centralized systems, which are limited by the capacity of a single machine, distributed systems can grow incrementally. Need to serve more users or handle more data? Simply add more nodes to the system. This ability to expand on demand enables services like search engines and streaming platforms to support millions of simultaneous users worldwide. Scalability is not just about size, it is about maintaining performance and responsiveness as demands increase, and distributed systems are specifically designed to make this possible. Reliability is another central goal. Distributed systems are built to be more resilient than single systems. If one node fails, a server crashes, a network link goes down, the rest of the system can continue operating, rerouting tasks and data as needed. This redundancy ensures higher availability, which is critical for services that people expect to be online at all times, such as online banking or healthcare systems. By avoiding a single point of failure, distributed systems greatly improve the chances that a service remains operational even when parts of it break down. Resource sharing is also a vital advantage. The computers that make up a distributed system can pool their resources, processing power, storage, data, and specialized devices so that each user or application can access what it needs when it needs it. This collective approach makes it possible to handle tasks far too large or complex for any single machine, such as scientific simulations, massive multiplayer gaming, or global e-commerce platforms. However, these remarkable benefits come with significant challenges that set distributed systems apart from their centralized counterparts. Perhaps the most fundamental is the complexity of managing multiple independent nodes that must coordinate over a network. Unlike a single computer that can share memory and synchronize tasks directly, distributed systems rely on messaging to communicate, and messages can be delayed, lost, or arrive out of order. This lack of a shared global clock makes it difficult to maintain consistency, ensuring that all nodes have the same view of the system at the same time. Partial failures are another unavoidable reality. In a distributed system, it is almost certain that at any given moment, at least one component is experiencing a problem, whether it is a hardware crash, a network hiccup, or a software bug. The system must be engineered not only to detect these failures, but to recover gracefully, rerouting work around the broken parts. Handling partial failure is one of the most challenging aspects of distributed system design, as it is rarely possible to guarantee that every node is always healthy and connected. Security becomes more complicated as well. With data and computation spread across many machines, often over public networks, the potential attack surface increases. Safeguarding data, ensuring secure communication, and managing access all become more intricate as the number of nodes grows and as systems span organizational or even national boundaries. Data consistency presents yet another hurdle. In a centralized system, there is typically a single, definitive copy of each piece of data. In distributed systems, copies may exist on multiple nodes to improve performance and reliability. But this raises the question, how do you ensure that all copies are up to date? Achieving perfect consistency across distributed nodes can be expensive or even impossible, especially in the face of failures or network delays. Designers must often balance consistency against other goals like availability and performance. Despite these challenges, the advantages of distributed systems are so compelling that they have become the backbone of modern computing. Their flexibility allows businesses to respond rapidly to changing needs, deploying new features or scaling services without massive upfront investment. The ability to distribute resources geographically brings services closer to users, reducing latency and improving user experience. In domains from e-commerce and healthcare to gaming and GPS navigation, distributed systems enable functionality that would simply not be feasible otherwise. The move toward distributed systems was gradual. Early examples include local area networks and technologies like Ethernet, which allowed multiple computers to share resources and communicate efficiently. Over time, as the internet connected more and more devices, distributed architectures evolved to meet the growing demand for global services. Today, even simple applications often rely on a sophisticated network of distributed components behind the scenes. Comparing distributed systems to centralized models helps clarify their unique strengths and weaknesses. Centralized systems are generally simpler to manage, easier to secure, and can be more predictable in their behavior. However, they suffer from limited scalability, a single point of failure, and can become performance bottlenecks under heavy load. Distributed systems, on the other hand, offer superior scalability, resilience, and performance, but at the cost of greater complexity, higher potential for security breaches, and increased difficulty in troubleshooting and maintaining data consistency. There are also decentralized systems, which fall somewhere between fully centralized and fully distributed architectures. These systems distribute control among several nodes but may not offer the same level of resource sharing or fault tolerance as true distributed systems. Each approach comes with its own trade-offs, and the choice often depends on the specific needs and constraints of the application. The business implications of adopting distributed systems are significant. Organizations can achieve cost efficiency by using commodity hardware, improve their ability to innovate and adapt, and offer services with higher availability and performance. However, they must also invest in the expertise and infrastructure required to manage the added complexity, ensure security, and address the unique challenges of coordination and failure handling. Ultimately, distributed systems are indispensable for the digital experiences that define our age. Their ability to scale, share resources, tolerate faults, and adapt to changing requirements ensures that they will remain at the heart of computing for years to come. While they introduce new problems and require sophisticated solutions, the benefits they bring, performance, reliability, and the power to connect people and services across the globe are simply too great to ignore. In every search, every streamed movie, and every online transaction, the invisible machinery of distributed systems is hard at work, quietly shaping the world we live in. Imagine a city at rush hour, where thousands of people move in all directions, communicating and coordinating with traffic lights, signs, and one another. In distributed systems, the digital equivalent of this city is shaped by its architecture, how its parts are arranged, and by the protocols and rhythms that govern how those parts communicate and cooperate. There is a vast diversity of approaches to organizing these systems, each with its own strengths and trade-offs, but all must address a fundamental challenge, enabling independent computers to work together as a coherent whole. One of the most influential architectural models in distributed systems is the client-server paradigm. In this arrangement, some computers, called servers, provide resources or services, while others, known as clients, request and use those resources. The model is straightforward. A client sends a request, and the server responds, often drawing from a central pool of data or functionality. This division of labor simplifies system design. Servers can be optimized for reliability, security, and performance, while clients can remain lightweight and focused on user interaction or local processing. Yet, the elegance of the client-server model comes with limitations. Because servers occupy a privileged position, they can become bottlenecks if too many clients compete for their attention. This centralization also means a server's failure can disrupt the entire system, prompting designers to seek ways to distribute the load or introduce redundancy. A contrasting approach is found in peer-to-peer or P2P architectures. Here, the distinction between client and server fades. Every node is both a provider and a consumer of resources. Instead of relying on a central authority, peers connect and interact as equals, sharing files, processing power, or other assets directly with one another. This decentralization offers several advantages. It can enhance resilience because there is no single point of failure, and can make better use of the collective capacity of all participants. However, coordination becomes more complex, as peers must find one another, resolve conflicts, and ensure fairness and reliability without a central overseer. P2P networks are especially attractive for applications where resource sharing and robustness are critical, but where tight central control is neither feasible nor desirable. Many real-world distributed systems do not fit neatly into these categories. Instead, they employ multi-tier or layered architectures. In these designs, software components are grouped into tiers, each responsible for a distinct aspect of the system's functionality. A common example is the three-tier architecture. The presentation tier handles user interfaces and delivers information to users. The application tier contains the core logic that processes requests and enforces business rules. Finally, the data tier manages the system's persistent storage, such as databases or file systems. By separating concerns in this way, multi-tier architectures make systems easier to scale and maintain. Each layer can be developed, optimized, or replaced independently, and additional tiers can be introduced as needs evolve, perhaps to handle caching, authentication, or analytics. This separation also improves security and manageability, since access to sensitive data or critical logic can be tightly controlled within specific tiers. The choice of architecture, client-server, peer-to-peer, multi-tier, or some hybrid, profoundly influences how the system's components communicate. At the lowest level, physical connections between nodes can take many forms: wired technologies like Ethernet, wireless networks like Wi-Fi, or even global-scale links over the Internet. These physical links are the highways and byways along which messages travel, and their reliability, speed, and topology all shape the system's performance. But the real magic happens above the physical layer, where distributed systems rely on middleware and protocols to turn raw network connections into meaningful interactions. Communication protocols are the agreed-upon languages and procedures that ensure messages can be sent, received, and understood across diverse hardware and software environments. Among the most important of these is Remote Procedure Call, or RPC. This protocol allows a program on one machine to execute code on another as if it were a local function, hiding much of the complexity of network communication. Message passing is another foundational mechanism, where nodes exchange discrete units of information, messages, without assuming shared memory or direct access to each other's resources. The choice of protocol depends on the system's needs. Some applications require direct, synchronous communication, while others thrive on asynchronous exchanges, where messages can be delayed, reordered, or handled in batches. Structured communication often involves well-defined channels and formats, ensuring predictability and reliability. In contrast, unstructured communication is more flexible but can make coordination harder, as messages may arrive unpredictably or from unexpected sources. Beyond simply moving messages from place to place, distributed systems must also coordinate. Coordination refers to the mechanisms and protocols that manage the interactions between concurrent processes, those running at the same time, possibly on different nodes. It is what allows a distributed system to behave predictably, even when parts of it operate independently or encounter failures. This coordination takes many forms. Consensus protocols are vital when nodes must agree on a shared course of action, such as which data is the latest or who should take on a leadership role. Replication mechanisms ensure that copies of critical data remain consistent across the system, even as updates occur and failures strike. Fault tolerance protocols help the system detect and recover from the inevitable problems that arise when operating at scale. Message passing is not just about delivery, but also about ensuring that events occur in the right order, or that dependencies between tasks are respected. A particularly thorny challenge in coordination is time. Without a shared global clock, distributed systems must rely on logical clocks or other synchronization mechanisms to track the order of events. Clock synchronization protocols help align the perception of time across nodes, enabling accurate sequencing and coordination without assuming that all machines' clocks are perfectly in sync. The importance of robust communication and coordination extends to the tools and practices used by human teams building and maintaining distributed systems. Research shows that structured communication rhythms, like regular meetings or coordinated use of messaging tools, are crucial for distributed software teams. When coordination is neglected, misunderstandings and inefficiencies can quickly multiply, just as they do among computers. Underlying all these mechanisms are the network protocols that enable message transmission. TCP, for instance, provides reliable, ordered delivery of data, while TLS adds security by encrypting messages in transit, resolves human-friendly names into network addresses, allowing nodes to find and connect with one another. Heartbeat mechanisms allow components to check whether their peers are alive and responsive. Leader election protocols help systems designate a coordinator when needed, and logical clocks keep track of the sequence in which events occur across the network. Modern distributed systems are not static. Many are built on top of dynamic infrastructures that can add or remove nodes in response to changing demands. Orchestrators like Kubernetes manage clusters of machines using load balancers to distribute work evenly and ensure smooth operation. These tools embody the architectural and communication principles developed over decades, adapting them for the scale and complexity of today's cloud, edge, and hybrid environments. Distributed data storage is another pillar essential for cloud and edge computing. Data must be partitioned, replicated, and kept consistent, often across vast distances and many independent nodes. The architecture of data storage systems draws on the same principles, layering, consensus, replication, and coordination, that underlie the broader system. In the end, the success of a distributed system hinges on the interplay between its architecture and its methods of communication and coordination. The architectural choices set the stage, defining how responsibilities are divided and how components relate. The protocols and coordination mechanisms keep the show running, ensuring that, despite independence and distance, the system acts as a unified, reliable whole. Each advance in architecture or protocol brings new possibilities, but also new challenges, as the digital city of distributed systems grows ever larger and more complex. In the intricate dance of distributed systems, three issues silently dictate the tempo: consistency, fault tolerance, and security. These concerns do not operate in isolation. Instead, they intertwine, shaping the very reliability and trustworthiness of the digital frameworks upon which modern society increasingly relies. To appreciate their significance, one must first understand that the central challenge in distributed environments is not merely sending messages or dividing workloads, but ensuring that the system as a whole behaves predictably, even as its individual parts encounter errors, delays, or hostile threats. Consistency, in this context, means ensuring that each node or replica within a distributed system maintains the same view of data at any given moment. The reality, however, is far from straightforward. Distributed systems operate in environments where delays and failures are expected, so different models of consistency have emerged to balance precision with practicality. At one end of the spectrum lies strong consistency, where the illusion of a perfectly synchronized single system is maintained. If a user updates a value anywhere in the system, all other users, no matter where they are, immediately see the same update. This approach, while intuitive, can stifle performance and scalability, especially when nodes are spread across vast networks. On the other hand, weaker consistency models accept that not all nodes will agree instantly. Eventual consistency, for example, guarantees that if no new updates are made to a piece of data, all replicas will ultimately reflect the same value, though there may be brief periods of divergence. Causal consistency strengthens this by ensuring that operations with cause and effect relationships are seen in the correct order, but it allows unrelated updates to be perceived differently across nodes. Other nuanced models include read-your-writes consistency, which ensures that after a node writes a value, it always sees that update in subsequent reads, and monotonic consistency, which guarantees that once a node sees a value, it will never see an older value later on. Each consistency model represents a different set of trade-offs between immediacy, performance, and complexity. Stronger models like strict serializability or linearizability ensure that the system behaves as though all operations occur in a single, well-ordered sequence. Sequential consistency allows some flexibility in the order of operations, as long as each individual process's operations are seen in order. Causal consistency, as discussed, guarantees the preservation of cause and effect relationships. Weaker models, such as session or eventual consistency, enable higher performance and availability, but require both developers and users to tolerate moments of inconsistency. The hierarchy of these models reflects a spectrum, from the rigid predictability of strong consistency through sequential and causal guarantees, down to the looser assurances of eventual or session consistency. But why is consistency so difficult to maintain? The answer lies in the very nature of distributed systems. When data is replicated across multiple machines, perhaps for reasons of performance, availability, or disaster recovery, each node must decide how and when to apply updates. Network partitions, hardware failures, or simply the vast distances between nodes mean that perfect synchronization is rarely possible. Thus, the system designer must choose which guarantees to offer and which limitations to accept, always aware that user experience, correctness, and system efficiency hang in the balance. Alongside consistency, fault tolerance stands as a pillar of distributed reliability. Fault tolerance is the system's ability to continue operating correctly, even when some of its components fail. In the world of distributed systems, failures are not rare events, they are the norm. Faults can be transient, flaring up and disappearing quickly, intermittent, recurring unpredictably, or permanent, requiring manual intervention to resolve. To survive these inevitable hiccups, distributed systems employ a range of strategies. Redundancy is perhaps the most fundamental approach. By duplicating critical components or data, the system ensures that if one part fails, another can take over. Replication, a specific form of redundancy, involves maintaining multiple copies of data or services across different nodes. This not only guards against data loss, but also improves availability and responsiveness, especially in large-scale systems. There are various replication strategies, each with its own advantages and drawbacks. In the primary backup model, one node serves as the primary source of truth while others stand by as backups. Multi-primary or multi-master replication allows several nodes to accept updates, increasing availability but complicating conflict resolution. Some systems prefer master-slave arrangements, where a designated master handles all rights, while others adopt masterless designs, distributing responsibility more evenly. Beyond replication, fault tolerance techniques also include failover mechanisms, automated processes that detect failures and redirect requests or tasks to healthy nodes. Systems may degrade gracefully, reducing functionality rather than failing completely, to preserve core services in the face of extensive problems. Checkpointing is another valuable technique, periodically saving the system's state so that it can recover quickly after a crash. Tracing and prediction, meanwhile, help administrators spot developing issues and intervene before they escalate. Yet, ensuring that multiple replicas stay consistent, especially in the presence of failures, is no trivial matter. This is where consensus algorithms enter the stage. Distributed consensus is the process by which a group of nodes agree on a single value or course of action, even if some members are faulty or messages are dropped. Reliable consensus is vital for maintaining both consistency and availability. It enables distributed databases to agree on which transactions to commit, orchestrates leader elections, and coordinates configuration changes across the system. Two of the most influential consensus algorithms are Paxos and Raft. Paxos, regarded as foundational, is known for its theoretical robustness but is often considered difficult to understand and implement. Raft, by contrast, was designed with readability and practical deployment in mind. Both algorithms divide the consensus process into clear phases. Nodes propose values, others accept or reject, and a decision is eventually reached. While their internal mechanics differ, Paxos emphasizes a minimalistic core protocol, whereas Raft introduces explicit leader election and log replication. Both aim to ensure that, despite failures or delays, the system as a whole moves forward in agreement. The choice between Paxos and Raft is often a matter of context and priorities. Raft's clarity and modularity have made it popular in modern distributed databases and storage systems, while Paxos remains a touchstone for theoretical work and highly specialized deployments. Regardless of which protocol is used, the ability to reach consensus underpins the reliability and consistency of distributed systems in the real world. All these mechanisms, consistency models, replication, consensus, would be moot without robust security. Security in distributed systems is particularly challenging due to their expanded attack surface. Data and computation are scattered across many nodes, often spanning organizational or even national boundaries. Security goals in this domain include ensuring integrity, meaning data is not tampered with, confidentiality, meaning data remains private, and availability, meaning services remain accessible even during attacks or failures. To meet these goals, distributed systems employ a range of authentication mechanisms, such as multi-factor authentication, role-based access control, encryption, and single sign-on. These tools help establish trust between nodes, users, and services, ensuring that only authorized entities can access or modify sensitive information. However, distributed systems also face unique threats: the risk of compromised nodes, man-in-the-middle attacks during communication, and the difficulty of coordinating security policies across disparate environments. Consensus protocols themselves play a role in security by making it harder for attackers to subvert the system through a single compromised node. Cryptographic techniques such as digital signatures and secure hashing help protect data integrity and verify the authenticity of messages. Fundamental security principles like fail-safe defaults, open design, least privilege, and separation of privilege guide the design of secure distributed systems. These principles help limit the damage any single component or user can inflict if compromised, and ensure that the system's default behavior errs on the side of caution. In practice, securing a distributed system is an ongoing process. Administrators must constantly assess and update security policies, monitor for threats, and ensure that the system's architecture and protocols remain resilient as new vulnerabilities are discovered. The interplay between consistency, fault tolerance, and security is delicate. Measures to improve one can sometimes weaken another, requiring careful design and continual vigilance. Ultimately, the pursuit of consistency, fault tolerance, and security in distributed systems is a balancing act. Each decision, from the choice of consistency model to the implementation of consensus algorithms and the layering of security mechanisms, shapes how the system behaves in the face of uncertainty and adversity. These intertwined concerns define the trust that users, organizations, and entire industries place in the infrastructure that powers the digital world. As distributed systems continue to evolve, so too will the techniques and philosophies that guide their design, ensuring that they remain not just powerful and scalable, but also reliable and secure. Across the tapestry of modern technology, distributed systems serve as the quiet architects behind a staggering range of real-world applications. Their influence is everywhere, from the way healthcare data is processed and shared, to the infrastructure powering financial markets, to the seamless delivery of massive video files for global audiences. The reach of distributed systems now extends into nearly every major industry, with each field adapting the unique strengths of distributed computing to its own demands. In healthcare, distributed systems work behind the scenes to manage the flow of patient information, coordinate care across hospitals, and power sophisticated diagnostics. For example, medical imaging tasks that once took hours or days on a single machine can now be distributed across clusters of servers, dramatically reducing processing time. This same approach has transformed drug discovery and genomics, where vast data sets must be analyzed, compared, and securely stored across geographies and institutions. In physics, distributed systems have become indispensable for tackling problems of scale that were once insurmountable, such as simulating the behavior of subatomic particles or modeling the cosmos. Scientists routinely harness the collective power of thousands of nodes to crunch numbers, test hypotheses, and generate insights that no single computer could achieve alone. Video rendering and animation studios are also deeply integrated with distributed architectures. Creating a blockbuster film or a cutting-edge video game often requires rendering millions of frames, each a computationally intensive task. By distributing these rendering jobs across large server farms, studios can meet deadlines and push creative boundaries, delivering visually stunning results that would otherwise be impossible. This same architecture underpins online gaming platforms, where real-time responsiveness and reliability are paramount. Distributed systems ensure that players worldwide experience smooth gameplay, consistent worlds, and robust matchmaking regardless of their location. The business world has embraced distributed systems for their ability to manage, analyze, and extract value from massive amounts of data. In finance, distributed computing powers algorithmic trading, risk modeling, and fraud detection tasks that demand not only speed, but also unwavering reliability. The energy sector relies on distributed systems to balance power grids, process sensor data from renewable sources, and optimize resource allocation in real time. Manufacturing and retail industries use distributed databases and analytics platforms to track inventory, monitor supply chains, and personalize customer experiences at scale. Even in transportation, distributed architectures enable smart routing, fleet coordination, and predictive maintenance, helping to keep goods and people moving efficiently. At the heart of many of these advancements is cloud computing, which has become the most visible and indispensable manifestation of distributed systems. Cloud providers orchestrate sprawling fleets of servers spread across multiple data centers, offering resources on demand to organizations and individuals alike. These cloud environments are not monolithic. Rather, they are built on flexible, modular frameworks that allow customers to scale up or down, shift workloads, and deploy services wherever needed. Content Delivery Networks, or CDNs, exemplify this model by caching data in geographically dispersed locations, ensuring that users receive content quickly and reliably no matter where they are. Distributed databases form another pillar of this ecosystem. They support everything from global e-commerce platforms to real-time analytics engines, allowing organizations to store, retrieve, and process data across regions and continents with remarkable efficiency. These databases must balance the competing demands of performance, availability, and consistency, a challenge that distributed systems are uniquely equipped to address. The rise of streaming platforms, e-commerce giants, and the Internet of Things has only intensified reliance on distributed databases, as these applications demand not only scale, but also the ability to adapt rapidly to changing user behavior and workload patterns. One of the most innovative and widely discussed applications of distributed systems in recent years is blockchain technology. Blockchains are, at their core, distributed ledger systems that record transactions across a network of peer nodes, each maintaining its own copy of the data. This architecture is fundamentally different from traditional, centralized databases. In a blockchain, trust is decentralized. Instead of relying on a single authority, the system uses consensus protocols to ensure that all copies of the ledger remain in sync. Peer-to-peer overlay networks, cryptographic signatures, and consensus mechanisms work together to provide both security and transparency. The result is a system that is not only resilient to failure, but also resistant to tampering or centralized control qualities that are invaluable in areas such as digital currency, supply chain tracking, and digital identity management. The impact of blockchain extends far beyond its original application in cryptocurrencies. Financial systems are experimenting with blockchain-based settlement and clearing processes, while organizations explore its use for managing digital ownership, verifying identities, and automating contractual agreements through smart contracts. The scalability and security of these systems remain active areas of research as developers seek ways to increase throughput and address potential vulnerabilities without compromising the core values of decentralization and immutability. As distributed systems have become more entrenched in daily life, their architectures have continued to evolve. The emergence of edge computing marks a significant shift, moving computation and data storage closer to where data is actually generated, at the edge of the network. This approach reduces latency, conserves bandwidth, and enables applications that require real-time responsiveness, such as industrial automation, autonomous vehicles, and smart city infrastructure. Cloud computing, meanwhile, has grown increasingly sophisticated, with trends like multi-cloud networking and cloud-native development fostering greater flexibility and resilience. Organizations now routinely blend resources across multiple cloud providers, optimizing for cost, performance, and geographic reach. Serverless computing represents another transformative trend. In this paradigm, developers focus solely on building application logic, while the cloud provider manages all aspects of resource allocation, scaling, and fault tolerance behind the scenes. This model reduces operational overhead and accelerates development, but it also introduces new challenges in debugging, monitoring, and security areas that are now attracting significant research attention. Artificial intelligence and machine learning stand as both beneficiaries and drivers of advances in distributed systems. Training large artificial intelligence models requires distributing workloads over vast clusters of graphics processing units and specialized accelerators, a task that would be impractical without robust distributed architectures. Conversely, artificial intelligence is increasingly used to manage and optimize distributed systems themselves, automating resource allocation, detecting anomalies, and orchestrating complex workflows. This feedback loop between distributed computing and artificial intelligence is expected to deepen, opening new frontiers in both fields. Looking ahead, several trends are poised to shape the future of distributed systems. The concept of the data mesh, which treats data as a decentralized product and emphasizes domain-oriented ownership, is gaining traction as organizations grapple with the complexity of managing data at scale. Chaos engineering, a practice that deliberately introduces failures into systems to test their resilience, has become a vital tool for uncovering hidden weaknesses and building more robust architectures. Quantum computing is being explored as a potential disruptor, promising new forms of distributed computation that exploit quantum properties for speed and security. Meanwhile, the idea of decentralized autonomous organizations, or DAOs, is being investigated as a way to coordinate human and machine activities without traditional hierarchical management. These developments could fundamentally alter how distributed systems are designed, governed, and utilized. The rapid evolution of distributed systems brings with it new programming models and decision-making frameworks, as well as a need for improved methods of testing, debugging, and verification. As these systems grow ever larger and more complex, ensuring their correctness, security, and efficiency remains a formidable challenge. Sustainability is also emerging as a priority, with researchers and practitioners exploring ways to reduce the environmental impact of large-scale distributed computing. Advances in networking, such as more efficient protocols, containerization, and microservices architectures, continue to push the boundaries of what distributed systems can achieve. Staying abreast of these developments has become essential for organizations that wish to remain competitive and secure in an increasingly interconnected world. In sum, distributed systems have moved from the realm of academic curiosity to the foundation of modern civilization. Their applications span industries and continents, underpinning everything from scientific discovery to social interaction, commerce to critical infrastructure. As new technologies emerge and old ones evolve, the field of distributed systems is poised to remain at the forefront of innovation, reshaping not only how we build and use technology, but how we understand the very fabric of the digital world.